Hello and welcome to this lesson on the nuclear radius, which is part of the nuclear physics topic in AQA A-Level Physics. So in today's lesson we're going to look at how you can calculate the nuclear radius from experimental values. So if we've been successful in Learn today, we should be able to detail how the value of the nuclear radius was discovered, understand how the nuclear radius equation was derived, and then detail how the nuclear radius equation allows us to understand nuclear properties, which links into the following part of the AQA A-Level Physics specification 3.8.1.5 nuclear radius. So in previous lessons we've considered the size of the nucleus in an atom. Now Rutherford estimated the size of the nucleus in his Rutherford scattering experiment, where he fired alpha particles at gold nuclei. So here an alpha particle was fired near to the gold nuclei in the investigation. But what issues does this result have for the nuclear radius? Well, in this Rutherford scattering experiment, the alpha particle is repelled by the positive charge of the gold nucleus because it is also positively charged. So the kinetic energy of the alpha particle turns into electrical potential energy due to the repulsive force between the two charged objects. Now, this tells us that this value that we've calculated is not the nuclear radius, but in fact the distance of closest approach between the alpha particle and the nucleus. So this value could be changed with the energy of the alpha particle. So the more kinetic energy in the alpha particle, the closer it could get. So this tells us we're not actually measuring an accurate value for the nuclear radius. So we need a different way to measure the radius of the nucleus, because if we have a higher kinetic energy in our alpha particle, the nuclear radius in this instance will be smaller because the distance of closest approach will be smaller. So you can get a high distance of closest approach if you've got a low kinetic energy in your alpha particle, because there's less kinetic energy to change into electrical potential energy, so the conversion occurs further away from the nucleus. Whilst if your alpha particle has a high kinetic energy, you've got a small distance of closest approach because there's more kinetic energy to change into the electrical potential energy, so the conversion would occur closer to the nucleus. So this shows that we can't actually get one standard value for the nuclear radius by this method, because it depends on the kinetic energy in the alpha particle, so there must be a different way needed to measure our actual nuclear radius. So to work out the actual size of the nucleus, we can carry out an experiment called the deep inelastic scattering of electrons. Now this was known as the Davidson-Germer experiment and was conducted between 1923 and 1927, which confirmed both the de Broglie hypothesis and the nuclear radius. So by confirming the nuclear radius, the experiment was an important historical development in the establishment of the chain nuclear fission event, and by demonstrating the wave particle duality with the de Broglie hypothesis, this experiment was an important historical development in the establishment of quantum mechanics and of later the Schrödinger equation. So, the electron diffraction apparatus has a basic similarity with the alpha particle scattering carried out by Rutherford. So, electrons are fired at a thin film of atoms. In the first experiment, they used graphite. Now, electrons are used because they do not interact with the strong nuclear force of the nucleus, whilst neutrons, protons, alpha particles do, because electrons are leptons and are not hadrons. So, because of this case, the electron diffraction is an accurate method for measuring the nuclear radius, because they're not going to be influenced by the actual interactions produced by the nucleus. So in a similar fashion to the Rutherford scattering experiment, the electrons are fired at a thin sample of atoms and the path they take afterwards is then traced. So it's important to know what's going on. So the electron the electron can take a path which is influenced by two different factors. The electron path is influenced by both the scattering effect and the diffraction effect. Now this diffraction effect shows that the electrons have wave-particle duality, and the de Broglie wavelength of an electron to carry this out must be very small when we investigate our nuclear radius, so this means we've got to fire our electrons with a very high energy. So let's firstly look at the Rutherford scattering effects. So when the electron passes very close to the nucleus, the electrostatic force causes an attractive deflection of the particles. So this means that the pattern detected is similar to the one found in the Rutherford scattering. So the electrons deflect towards the nucleus, which is actually the opposite effect observed by Rutherford in his alpha particle scattering experiment. This deflection occurs because the negatively charged electrons are attracted to the positively charged nucleus. So even though the type of electrostatic attraction is different, the path pattern is actually the same as the Rutherford scattering results. The second effect is diffraction. So when the electron passes through the graphite structure, the electron gets diffracted. So for diffraction to occur, the electron must be exhibiting wave behavior. So the electron must have a de Broglie wavelength. So for the most diffraction possible, the gap between the actual graphite atoms must equal the de Broglie wavelength. So here the gap is actually the nucleus of the atom. So we can approximate the gap. We can approximate this gap to be between the nuclei because the diffraction takes place around the edges of the nuclei in which the electron wave moves between. So as the electron is acting like a wave for this diffraction effect, we can work out its wavelength with the following equation. The de Broglie wavelength is equal to Planck's constant times by the speed of light divided by the energy of the alpha particle. So actually the fact that diffraction occurs shows us that Rutherford was actually very fortunate when he carried out his alpha particle scattering experiment, because unbeknownst to him that the de Broglie wavelength of the alpha particles that he used was actually quite small, and the Coulomb repulsion stops it getting too close to the alpha particle to diffract through. Now he was very lucky, because otherwise if you did get this diffraction effect in the Rutherford scattering experiment, this would have confused the data and he would not have been able to work out the nuclear structure which he carried out in 1911. So here we can see a graph of the electron scattering results gained when we fire electrons through our graphite structure. Now you'll notice the minimum angle, which is the dip in the graph, is important, as this must be the angle at which diffraction occurs. Now you can see you get your shape because our pattern is influenced by both the scattering effect, which is our curved line at the top right hand side, and our diffraction effect, which is our number of bumps or peaks, which is shown in the bottom right hand side. So this indicates to us that this bottom out, the first section, is the angle at which diffraction takes place. So we can use this measurement to then determine the gaps between the nuclei and therefore get a value for our nuclear radius. So please do remember that this overall pattern is a combination of both the diffraction due to the de Broglie wavelength but also the Rutherford scattering experiment. So the electron scattering clearly shows features of both Rutherford scattering due to the electrostatic interaction and diffraction. Now we can consider these results due to the diffraction of the electron that it must be exhibiting wave behavior. So if we concentrate on the minimum we've pointed out earlier, it suggests that the nucleus is behaving as a circular object of diameter d. So we can use this to find a value of the nuclear radius, and we can use the diffraction equation which you've covered previously in our waves topic. So we know that sine theta is equal to lambda over d. Now please remember, this is a simplified version of the equation covered in the waves topic because there's no n term, because there are no orders of diffraction found here. It's just n equals 1. Now also, please remember that d is our nuclear radius and lambda is the de Broglie wavelength of the beam of electrons. Now we can further derive this equation to make it even more accurate, because by applying wave theory to plane waves passing through at normal instance through a circular gap, which is what we assume the nucleus is going to be like, we can get a correction term of 0.61, which we can apply to our equation, where we can say sine theta is equal to 0.61 lambda over d. But we've got to remember that if the minimum angle due to diffraction is measured and the de Broglie wavelength can then be calculated, then the nuclear radius can be found, which is given as d in the equation. Now remember, each high energy electron is diffracted by an individual nucleus. This isn't the same as electron diffraction covered in the particles and radiation topic, which is where electrons are diffracted between atoms. This is why our equation is for a minimum value and not a maximum value. So let's just recap our main methods to work out the nuclear radius. We have the Rutherford scattering method and we have the electron diffraction method. Now we've got to remember that for the Rutherford scattering method, it finds the distance of closest approach, whilst the electron diffraction method finds the nuclear radius. The Rutherford scattering fires alpha particles at gold nuclei, whilst electron diffraction has electrons fired at carbon nuclei. In Rutherford scattering, you get repulsive scattering due to the alpha particles and the gold nuclei having the same charge, whilst for electron diffraction, you will get attractive scatter as the negatively charged electrons are fired at the positively charged carbon nuclei. Now, Rutherford scattering relies on the particle properties of matter, whilst electron diffraction relies on the wave properties of matter. Now, Rutherford scattering has the major conclusion of backscatter, leading to the idea that the nucleus must be extremely small compared to the size of the atom, whilst diffraction is the major conclusion in the electron diffraction method, which shows us both electrons are acting as a wave and also allows you to work out the value of the nuclear radius. Now, electron diffraction can be used to measure the nuclear radius r for samples of various elements. Physicists then use this to find a relationship between r and the mass number of the element A, and this was carried out by plotting a graph of the nuclear radius r against the mass number A. And what we got is as follows. We found that if we plotted a graph of r against a to the power of a third, then this gives us a straight line through the origin with a gradient equal to a constant which we'll call r0. So plotting this graph can allow you to derive an accurate value of r0. Also, it will be interesting to note that a graph of log r against log a gives a straight line with a gradient of a third and a y-intercept equal to r0, which confirms the relation between A and r is linked by a power of a third. Now, this relationship is linked by a power of a third as the nucleus is a spherical shape and the volume of a sphere has a power of a 3 in it. Now, we can also look at our graph of r against a. So for the experimental results, we can see a graph of r against a plotted like the one below, and this shows us that r does not depend on a, but rather a to the power of a third. So when they plotted the graph of r against a to the power of a third, they found a straight line that cut through the origin and had a gradient of r0. Now, r0, by the way, is a constant representing the radius of a single nucleon and has a value on average between 1.2 and 1.5 femtometers. So we can say our equation we've got to learn is that the nuclear radius big R is equal to our constant r0 times by a to the power of a third, where a is the mass number of the nucleus. So the radius of a nucleus has been found to be that particular equation, where we can say for AQA examinations our standard value for r0 is 1.05 femtometers, where we say a femtometer is 10 to the minus 15 meters. Now, it's also important to note that there's no standard value for r0 as it represents the radius of an average nucleon in a nucleus. Now, there's no consistent value because there's different numbers of neutrons and protons in each nucleus, leading to a different average nucleon number. So let us have a look at how you would answer a question based on electron scattering experiments, because we can use our data to derive the nuclear radius. So for example, if the electron beam energy is 80 mega electron volts and the first diffraction minimum occurs at about 26 degrees, calculate the nuclear radius of a nucleus which diffracts the electrons. So the first step is converting your beam energy from MeV into joules. Now, that conversion is by firstly converting MeV into EV, which is times by 10 to the 6, then multiply by 1.6 times 10 to the minus 19 to get it into joules. The second step is then to work out the momentum of the electron. Now, the momentum of the electron is equal to P is equal to E over C, where C is the speed of light. So we can take our energy and divide it by the speed of light to get our momentum. We can then use this to work out the de Broglie wavelength of our electron, because we know that the de Broglie wavelength is equal to Planck's constant 6.63 times 10 to the minus 34 over the momentum which you've just worked out. Then finally, we can then use the diffraction equation to derive our slit gap, which we can just say is our nuclear radius. So we say sine theta is equal to 0.61 lambda over d. So therefore d is equal to 0.61 lambda over sine theta. We know theta in this case to be 26 degrees. We've worked out the de Broglie wavelength lambda to be 1.6 times 10 to the minus 14 meters. Pop our our value in and we get 2.2 times 10 to the minus 14 meters. Now a couple of things to note. In step 2 we did use a relativistic equation to work out our momentum, which may be the first relativistic equation that we have encountered, that P is equal to E over C. And then also please do remember that we were given our angle in degrees, so we've got to be using degrees here, so don't have your calculator in radians mode. So what can we summarise from today's lesson? We can estimate a radius of the nucleus from the closest approach of alpha particles and then determine our radius from electron diffraction. We should have knowledge of typical values of the nuclear radius and we understand how the Coulomb equation can be used for the closest approach estimate. We can then understand our dependence of radius of the nuclear number with R equals R0 a to the power of third derived from experimental data. So if we've been successful and learnt in today's lesson, we should be able to detail how the value of the nuclear radius was discovered, understand how the nuclear radius equation was derived, and then finally detail how the nuclear radius equation allows us to understand nuclear properties. So thank you very much for watching today's lesson on the nuclear radius, which is part of the nuclear physics topic in AQA A-Level Physics. Thank you very much for watching and have a lovely day.